In this video, we are going to be looking at ionic product of water, pH, pOH, and pH scale. Water is a very weak electrolyte and it is only partially ionized according to equation 1. And if you don't say that, you can make it to be auto-ionization, or what we call self-ionization. Now, auto-ionization is when two water molecules react to form hydronium ions and the hydroxyl ion. And if we are to apply the law of mass action to equation 1, the law of mass action says at a constant temperature and at equilibrium, for any reversible reaction, there is a fixed relationship between the molar concentration of the products and the molar concentration of the reactants. So applying the law of mass action to equation 1 gives us an equilibrium constant K, given by the product of the molar concentrations of hydrogen ions and that of the hydroxyl ions divided by the molar concentration of water. But water is a very weak electrolyte, and it is only going to be dissociated to a very small extent, such that the concentration of undissolved water or unionized water will actually be regarded as a constant, or almost remains a constant. So when we cross multiply this, we get the K, the equilibrium constant, multiplied by the molar concentration of water, giving us the product of the molar concentration of hydrogen ions and the molar concentration of the hydroxyl ion. So we take that assumption. Water is a very weak electrolyte and the extent of ionization is very small. So water almost remains at the same concentration as at the start. So if we multiply the K, the equilibrium constant, with molar concentration of water, we obtain a new constant called Kw, which is the ionic product of water. So we can say the molar concentration of hydrogen ions multiplied by the molar concentration of hydroxyl ion will be giving us the ionic product of water. Now, at 25 degrees Celsius, the value of Kw is 1 exponent negative 14 moles squared decimeter per negative 6. And we know water at 25 degrees Celsius is neutral. In fact, water in nature is neutral, which means it has the same amount of hydrogen ions and the same amount of the hydroxyl ions. We can call that to be maybe X. So if the pure water is neutral and it has the same amount of hydrogen ion and the hydroxyl ion, substituting in that equation for ionic product, this would give us that the product of molar concentration of hydrogen ions and that of hydroxyl ions would be equivalent to X squared, which is actually the same as the ionic product of water, that is 1 exponent and negative 14. So to get the molar concentration of either the hydrogen ions or the hydroxyl ion, we just get the root of the Kw, and that would give us X as exponent negative 7 moles per decimeter cubed. So this implies that pure water at 25 degrees Celsius will be containing exponent negative 7 moles of hydrogen ions per liter, as well exponent negative 7 moles per liter of the hydroxyl ions. That's why it is neutral. So let's now go ahead and find out the pH of water. Now the pH, by definition, is the negative logarithm of the molar concentration of hydrogen ions that a solution produces. So if you look at a pH of any solution, we just get negative logarithm to base 10 of the molar concentration of hydrogen ions that is contained in that very solution, and mathematically we can express it as pH is given by negative log molar concentration of hydrogen ions. Or the other alternative definition is pH is the logarithm of the reciprocal of molar concentration of the hydrogen ions produced by a given solution. Mathematically, we can get it as pH is given by log to base 10 of 1 out of molar concentration of hydrogen ions. But now pure water at 25 degrees Celsius contains 1x per negative 7 moles per liter of hydrogen ions, and if we are to substitute that in our equation for pH, that is going to be negative logarithm to base 10 of 1x per negative 7, and the value we obtained there, if you press in your calculator, is going to be 7. And that's why we say the pH, or the neutral pH of water at 25 degrees Celsius is 7. It is just 7 at 25 degrees Celsius, to take note of that. When the temperature changes, the neutral pH will be changing, as we shall explain later. Now, something to note is when we add a small amount of acid to water at 25 degrees Celsius, the ionic concentration product, that is the molar concentration of hydrogen ion multiplied by the molar concentration of hydroxyl ions, will remain constant, but the concentration of hydrogen ions will increase while that of hydroxyl ions will reduce. So if the concentration of hydrogen ions are now more than the one of the hydroxyl ion, it implies the solution is going to be acidic. Similarly, when we add a small amount of base, the concentration of hydrogen ions will reduce and that of hydroxyl ions will increase, which means the solution is going to be alkaline, or the solution is going to be basic, but the ionic product will remain constant provided the temperature is kept constant. The dissociation of water molecule is actually an endothermic process. That's why we are emphasizing the element of constant temperature, that the temperature must be maintained constant. So if we increase temperature, we expect the value of Kw to also increase, because increase in temperature will favor the forward reaction, and the forward reaction is leading to increase in the amount of hydrogen ions and the hydroxyl ions. So the value of Kw will increase. So if the concentration of hydrogen ions and hydroxyl ions have both increased, the solution is still neutral, or the water is still neutral. We simply say pure water is neutral at a higher temperature. But will the pH remain the same? Definitely no, because the molar concentration of hydrogen ions has been increased. Therefore, we expect the neutral pH of water at a temperature higher than 25 degrees Celsius to be less than 7. But the water is not acidic, it is just neutral, and it will be higher than 7 when the temperature is lower than 25, because decrease in temperature will favor the backward reaction, that is the combination of hydrogen ions and hydroxyl ion to produce water molecules. In all cases, water will of course remain neutral so long as the molar concentration of hydrogen ions and that of hydroxyl ions are still the same. Okay, now let's establish the relationship between pH, pOH, and the pH scale. From what we have learned from the previous slide is that the ionic product of water is equivalent to 1 exponent negative 14, and we go mathematical a bit. Let's say we are taking logarithm to base 10 on both sides. This will give us logarithm of the product of molar concentration of hydrogen ions and that of hydroxyl ions equaling to logarithm to base 10 of Kw. So we know if you have log of A times B is the same as log of A plus log of B. So we simply obtain on the left hand side logarithm of molar concentration of hydrogen ions plus logarithm of molar concentration of hydroxyl ion, which is equating to logarithm of Kw. Then now if we multiply throughout the equation by -1, that will not change the meaning of the equation. The equation will remain the same. We come up with negative logarithm to base 10 of molar concentration of hydrogen ions plus negative logarithm to base 10 of molar concentration of hydroxyl ions, which is equaling to negative logarithm to base 10 of Kw. Then you remember definition of pH is the negative logarithm to base 10 of hydrogen ions concentration. So which means we already have pH on the left hand side. So what if we have negative logarithm to base 10 of hydroxyl ion concentration? That will be the pOH. So similarly on the right hand side of the equation we shall be having pKw. Hence pH plus pOH is equivalent to pKw. But we already know the value of Kw at 25 degrees Celsius. Kw is 1 exponent -14, and if we substitute into negative logarithm of Kw, we shall be getting our answer as 14. So pKw is 14, so our equation can simply be written as pH plus pOH is equivalent to 14, and therefore the pH scale at 25 degrees Celsius is going to be ranging to a maximum of 14. And which means at any one point, if you have the value of pH and you're supposed to find the pOH, you simply have pOH equaling to 14 minus pH. Or if you have the pOH and you want to obtain the value of pH, you simply get 14 minus the pOH, and that will be it. So I want us to summarize this by looking at the variation of the Kw with temperature. We have some data obtained at 0 degrees Celsius, at 10 at room temperature, and at 100 degrees Celsius. And I've worked out the molar concentration of hydrogen ions or hydroxyl ions, so that we are able to find the neutral pH at that temperature, as well the estimated pH scale for that particular temperature. You look at 0 degrees Celsius, the Kw is 1.1 exponent -15 moles squared decimeter per -6, and if you get the molar concentration of hydrogen ions or hydroxyl ions, which is X, is given by the root of Kw. You can put that in your calculator. You have 0.11 exponent -14 root, and that would give us 3.3166 exponent -8, which is roughly 3.32 exponent -8. That would be the molar concentration of hydrogen ions or the molar concentration of hydroxyl ions. So let's get the pH. That would be negative logarithm of our answer, and the answer we get there is 7.479, which we can round off to approximate to 7.48. And we have already seen that if we have pH and pOH, we shall sum them up to get the pKw, and in this case it's going to be 7.48 plus 7.48, giving us a pH scale of maximally 14.96 approximate. Then at 10 degrees Celsius we have 3.1 exponent -15, and we get the square root of that will be giving us a 5.5678 exponent -8, which is roughly 5.57 exponent -8. And if we get the pH, negative logarithm of that answer is going to be 7.25 roughly, giving us a pH scale totaling to 14.5. And at 25 degrees Celsius is what we have just finished. You can see the pH scale is maximum at 14. And then at 100 degrees Celsius, we can see that the Kw value is now higher. That is 7.5 exponent -14. If we get the root of that answer, we get a 2.7386, which is roughly 2.74 exponent -7, and we get negative logarithm to base 10 of that answer, we shall be getting 6.562, which is roughly 6.56 as our pH at that temperature, the neutral pH. And for us to obtain the pH scale, we're just going to sum up the two values, that is the pOH plus a pH. Remember, the hydrogen ions has the same concentration, so of course the pH is also 6.56. This will give us 13.12 as the pH scale. So you can see that the water is still neutral at different temperatures, but at different pHs as well. So we cannot say always pH of neutral water will always be 7. No, when the temperature changes, the neutral pH will also change, but the water will never become acidic unless it is impure. For pure water, it will always be neutral at any temperature. Thank you so much for following up this session. I hope you have enjoyed. I kindly remind you to subscribe to my channel, turn on the notification bell so that when I load the next session, you are able to be informed. And if you have any concern that you feel you want to share with me, I have my email, I have my WhatsApp number on the screen, or you can kindly put it on the comment section. I hope to see you next time, and thank you so much for this moment with you.